The term mole is a unit that represents the quantity 6.022 times 10 to the 23rd, which is also known as Avogadro's number. Because moles represent a uniform amount, they're convenient for comparing molecular scale quantities, like the numbers of molecules that participate in a reaction, or the numbers of molecules that float around in solution. For example, a molarity, which is abbreviated with a capital M, expresses how many moles of molecules are found in a liter of solution. The number of grams needed to prepare 1 mole of a salt, like sodium chloride, is its molecular weight, which can be derived by adding together the atomic weights of the 2 elements found in the salt. Sodium, which has a molecular weight of 23, and chloride, which has a molecular weight of 35.5. These sum together to give a molecular weight of 58.5 grams for the salt. So that has units of grams of salt per mole of salt, and this value is used as a conversion factor in our calculations. You can find atomic weights on a periodic table, but for convenience I'll provide you with a table of common atomic and molecular weights to use on the assessment, similar to this one. These atomic and molecular weights are for ions that are commonly used to make up salts, and you will have a table like this on the assessment, maybe not the exact same one. You'll not be told which of the ions are positively charged or negatively charged. Remember, those positively charged ions are referred to by the term cation, and the negatively charged ones by the term anion. So you won't be told which ions are cations and which are anions, and you'll not be told what the charges are on the ions, or how to use them to derive the molecular weight of a salt. These are all things you need to memorize. Also, the ions that you get on the table on the assessment may be ordered differently than the ones here. So make it a point to match the ions with their charges and not just memorize the order of the charges on the table, or it may be an unpleasant surprise on the assessment. To determine the molecular weight of a salt, you need to determine the ratio of cations to anions in the salt structure. Salts are different from individual molecules, like covalent compounds. Salts form an extended lattice or crystal structure that consists of cations and anions held together by ionic bonds. The molecular formula for a salt is really an empirical formula that expresses the ratio of cations to anions in the lattice. You can come up with this formula by writing out the cation and anion that make up the salt, like calcium and carbonate in this example, and note what their charges are as superscripts. You then crisscross the superscripts to give the subscript that each ion will have in the crystal structure. In this case, we have calcium 2, carbonate 2. And now you reduce the subscripts just as we did when we were calculating ratio strengths. And you do this by dividing both subscripts by any factor that they have in common that's greater than 1. In this case, you can divide both subscripts by the number 2. So dividing this by 2, dividing this by 2, and you get subscripts of 1 for each of the ions in the salt. In the final formula, note that you only include numbers that are greater than 1 in that formula. So to get the molecular weight of this formula, you would add together the atomic weight of calcium, which is 40, and we have one of those, plus the atomic weight of carbonate, which is 60. We have one of those. And so you get a total molecular weight of the salt of 100, and that would be in grams per mole, and we can now use that in calculations. So let's apply what we've learned in these examples. First question asks what's the molecular weight of calcium citrate? And so you're going to bring in your head what these charges are on the individual ions. Calcium has a charge of 2, citrate has a charge of -3, and you would crisscross those superscripts to get the subscript, or the number of ions in each unit of salt. So 3 calciums, 2 citrates is what we've got there. So to get the molecular weight, we would do 3 times the atomic weight of calcium, so 3 times 40, plus 2 times the molecular weight of citrate, or 180, to give 490 grams per mole. Okay, so you use the numbers of ions times by their atomic or molecular weight. So there's our molecular weight for the calcium citrate salt. Next question, how many grams of calcium citrate are required to obtain 0.08 moles of the salt? So we can set up a proportion now using the molecular weight of calcium citrate as the conversion factor. 498 grams of salt per 1 mole of salt. So how many grams of salt are needed to make 0.08 moles of the salt? So we can don't need to cross there. 0.08 times 498 grams gives us 39.8 grams of calcium citrate to get 0.08 moles of the salt. Last example question, what's the molarity of a 250 gram per liter solution of calcium citrate? So molarity was defined on that first slide. Capital M, it's the moles of compound per liter of solution. And we already have our compound dissolved in 1 liter of solution. So we just really have to figure out how many moles are represented by 250 grams. So we set up our proportion again. 490 grams of salt per mole of salt. 250 grams is how many moles? Crisscross, divide by 498. X is 0.5 moles of calcium citrate. So 250 grams is 0.5 moles. You can put that in here. 0.5 moles divided by 1 liter. That's 0.5 molar solution. Molarity is 0.5. All right, take a look at the next slide of problems, give them a try, and I will work them out in the next video.